Okay, so today is the day you've all been waiting for. I've been talking about it for weeks, and we've been anticipating the introduction of logarithms. Well, today's the day. It's going to be so exciting. Now, to add to the excitement of logarithms, my dog Harlow decided to join me today in the lesson, so you might hear her snarkling in the background. Say hi, Harlow. There's Harlow. She says hi. So our essential question today is, what is the inverse of the exponential function f of x is equal to b to the x power, where b is greater than 0 and b cannot equal 1? And what is the value of f inverse of b to the m for any real number m? So we're going to be taking a look at the exponential function and its inverse today, which is called a logarithm. Now, a logarithm is an exponent written instead of from the perspective of the outcome of raising a number to some power. It's instead written from the perspective of the exponent itself. Now, the exponential function f of x is equal to 2 to the x power is, as I said before, it's written from the perspective of the result. So, for instance, if we said, x was, 3, 2 to the third would equal 8. This is written from the perspective, or written where 8, which is the outcome, is all by itself. And it's saying that that is equal to 2 to the third power. Now, a logarithm is written from the exponent's perspective. So, like in this case, it would be written from the perspective of the 3. And it would say the log base 2 of 8 equals 3. And so what it's really saying is, if I raise 2 to the third power, I get 8, but I'm saying it in a different way. I'm saying it from the perspective of the exponent. In other words, the exponent is all alone by itself. And remember, when we studied inverses, we said basically they're just the function that's written from the perspective of the other variable. And that's what's going on here. So instead of writing it from the perspective of f of x, we're instead writing it from the perspective of x, which is the exponent. So today we'll learn to write something in log form from exponential form, and we'll learn to go from log form to exponential and exponential to log form. So we'll learn to do conversions. We're going to take a look at the graph of a log function, and we're also going to solve some problems that involve logarithms. So on the graph here, you'll see the very familiar graph of f of x equals 2 to the x power. So you'll see various powers of x represented in the points on this graph, and you'll see that customary exponential growth curve that we've been studying about and transforming that has the x-axis as its asymptote, or y equals 0. And you see that as you go to the right, the graph is increasing. So let's say we took some of those coordinates on the graph and we reversed them. So for instance, the one that I see highest up is at 3, 8. So if I reverse that and I graphed 8, 3, so that would be 8 right and 3 up. And that point right there would be the reflection of 3, 8 over the line y equals x, which hopefully you recall that inverses are always reflections of each other over this kind of imaginary reflecting line y equals x. And so if I were to take these points and reverse them, so take 3, 8 and reverse it to 8, 3, take the 2, 4 and reverse it to 4, 2, and I took the 1, 2 and reversed it to 2, 1. And then if I took the 0, 1 and reversed it, would be 1, 0. and the negative 1, 0.5, that would be 0.5 or a half, and negative 1, that would take me right here. And then the negative 2 and the 0.25 and reversed it, that would be 0.25 and negative 2. And I would just keep getting closer and closer this time to the y-axis. And my graph would look like this. And that is the graph of the log base 2 of x. And that's the inverse of f of x. That's the inverse of 2 to the x. Now when you think about those ordered pairs, essentially what they're saying is if the output of raising to the exponent is 8, the exponent must be 3. So if I were to say substitute that 8 in for x here, I'd be saying the log base 2 of 8 is equal to the output, which would be 3. So in other words, when I raise 2 to the third power, I get 8. And that's a really easy way to look at how you can convert from a log form to an exponential form is you start at that little 2, which is called a subscript. And again, the way we read that is log base. We say that that's the base. And remember, 2 is the base of the exponential function also. So the base, it's saying that the base is 2 and the exponent, which is on the other side, is 3, then the result must be 8. So again, this is right there is the base. This is the exponent that it's being raised to. And then the 8 ends up being the result. So again, it's saying f of x is equal to 2 to the x, just in another way to say log base 2 of x equals f inverse of x. Really quick, let's take a look at these labeled points and see if we can answer example B. So f inverse of 0.25 is equal to the log base 2 of 0.25, which means when I raise 2 to what power do I get 0.25, which 0.25 is really like 1/4, right? So the power I'd have to raise 2 to get that 1/4 would be negative 2. And that's where that 0.25 and negative 2 for the output is coming from, that ordered pair 0.25 comma negative 2. When the input is 0.5, in other words, when I'm saying I get 0.5 from raising 2 to some power, what must the exponent will be? Well, that's the same as 0.5 is the same as a half, so that would be an exponent of negative 1. If the input is 1, I'm saying the log base 2 of 1 is what? So 2 to what power is 1 would be 0. So again, what I'm answering is what's the exponent that I'd have to raise 2 to get this output of 1. Log base 2 of when the input is 2 would have an exponent of 1. In other words, 2 to the first power is 2. Log base 2 of 4, if the input's 4, would be saying if I raise 2 to the second power, I would get 2. Get 4. And then log base 2 of 8 means if I would raise 2 to the third power, I would get 8. So let's try to kind of go beyond that and find another point that's not on the graph. If f inverse of 16 is saying log base 2 of 16 would equal what? Well, so in other words, I'm wanting to know 2 to what power, question mark, equals 16. Well, I know that 2 to the fourth power is 16, so log base 2 of 16 must equal 4. Okay, so let's go ahead and turn the page. Aw, this page is not nearly as cute without my puppy on there. Okay, so let's recap the two different forms, exponential versus logarithmic form. So in exponential form, we list the base raised to some power equals a result. So for instance, 3 to the fourth equals 81. And in logarithmic form, we write it with the exponent by itself, and we say log. And of course the base of this exponent is 3, so that would be log base 3. That's my subscript. And then the exponent goes on the other side by itself, so there's the 4. So how this would be read would be log base 3 of 81 is 4. In other words, when I say the log, I'd say like the exponent that base 3 would have to be raised to get 81 equals 4. And again, a quick way to check that is to do a little circle around. You start at the base, the subscript in other words, and you do a little circle around. You say the base raised to that power would equal that result. And that makes it actually a really easy thing to go from log form to exponential form. You just kind of do that little circle around trick. I learned that much later on in life. I wish I had known that when I first learned about logarithms. It made my life so much easier. So let's take a look at these tables here. They're going to teach us to kind of get comfortable with switching from one form to the other. And again, I think you'll see why later it's important to be able to go to log form and get that exponent by itself. So for instance, when we've been trying to solve for a variable that was in the exponent, we were like, we really couldn't do that algebraically because we couldn't get that exponent, that variable out of the exponent position. Well, now we can by writing it as a logarithm. So let's take a look at this first one. Exponential form is 4 to the third equals 64. And so in logarithmic form, it would look like this. Log base, well, the base is 4, right? The exponent is 3, so that goes by itself on the other side. And then the result is 64. So again, that would be read log base 4 of 64 is 3. In other words, the exponent that 4 would have to be raised to get 64 is 3. Shh. Hello. Shh. Dogs are so noisy. Now going the other way around, I said you could do that little circle around. We could start at the base, which is 5, and if I raise it to the negative 2 power, I'll get 1/25. So writing that in exponential form, it would be 5 to the negative 2 power equals 1/25. So here's another one that's written in exponential form. We want to write it in log form. So although it doesn't have a very familiar base, the base is 2/3, so it's log base 2/3. The exponent is p, so it's going to go by itself on the other side, and then q. So this is not one we can really evaluate or check. It's just using two different variables. But log base 2/3 of q is p. And then going the other way, again, I feel like this is the easier way is when you go from log form to exponential, because you can just do this little circle around trick. You start at the base, which is a half, and so I'd say 1/2, and then I do this little circle around deal to the n power, so my power would be the n, is or equals, and then the result, as I finish my circle around, would equal m. So m is the result of raising 1/2 to the n power. So here's where you're going to get a chance to try your hand at this. And so I want you to go ahead and pause the video now and take a moment to switch from exponential form to log form in each of these 4 examples. And when you've completed the task, tune back in to check and see how you've mastered this skill. Pause the video now. Okay, so thanks for giving those a try. Take a moment and check your answers and make a note of anything that you're still struggling with. Anything that once you see the answer now, if you still don't understand why what you wrote doesn't match up, just make a note and you can ask me when I see you in class. So let's go ahead and turn the page and continue on learning some more about logarithms. So first of all, we're going to take a look at finding some sort of familiar logarithms, things that we've probably worked with quite a bit. And so we're going to take a look at example A. And so this very first, so these are like really different, 1, 2, 3, 4 different questions. They want us to find the value of each logarithm. And so when I look at this first one, f of x is equal to the log base 10 of x. And so for this function, I guess there's, 3 in each, what they want us to do is find the value for the given input. So for instance, for this first one, they want me to find f of 1000. They're saying, so if I said f of 1,000, I'd say the log base 10 of 1,000, so I'd plug in 1,000 for x. And I want to know what is that value, what does that equal? And then the next one would be saying log base 10 of 0.01, which means 100th. What's that value? And then finally log base, oops, I didn't leave enough space for that, log base 10 of the square root of 10. And in each case, I'm trying to figure out what would be the exponent that I would have to raise 10 to get these outputs. So I know that to get 1,000, I'd have to raise 10 to the third power, because 10 to the third is 1,000. So I know the value of that logarithm is 3. I know in the next one, 10, so really this is like saying 1/100th, because that's the 100th place. So I know that 10 to the second would give me 100. So if I raised instead 10 to the negative 2, remember that negative would flip it, that'd give me 1/100th. And then recall that the square root of 10 is like saying 10 to the 1/2. That's really what this means. And so that kind of helps me to figure out that this must be 10 to the 1/2 power. That gives me the square root of 10. So again, we're just kind of thinking logically through on knowing what the result is and knowing what the base that we're raising to a power is, we can kind of reason through and figure out what the exponent has to be. So in this case, we were doing powers of 10. In the next example, we're going to be looking at powers of 1/2 instead. So it may help to think about the fact that a base of 1/2 is like saying, it's like a base of 2, but, to the -1 power. So that might kind of help. So when we want to evaluate this log base 1/2 of when the input's 4, if you think about it, instead if the base was 2, we would have to raise 2 to the second power to get the 4, right? So instead, if we raised 1/2 to the -2 power, the negative would flip it, and the 2 would square that, and I would get 4. So 1/2 to the -2 would be like saying flip that and then square it, and that would give us 4. And then, oops, the log base 1/2 of 1/32. Now that one's a little bit easier to think about, because now I'm just thinking, well, 1 to any power is still 1, but 2 to the 5th power is 32. So that kind of helps me to see, oh, this just must be 1/2 to the 5th power, because if I raise 1 to the 5th, I get 1, but if I raise 2 to the 5th, I get 32, and that would give me 1/32. Okay, so again, the base is 1/2, I'm raising it to the 5th power, and I get 1/32. Here I'm taking 1/2, raising it to the -2 power, and it gives me 4. And then the last one there is log base 1/2 of 2 square root of 2. Now that one's definitely kind of tricky, and it might actually help to think about 2 square root of 2 in its maybe unsimplified form. And that's actually the same as saying, like if I brought the 2 back in underneath, that would actually be the square root of 8. Remember that 2 square root of 2 is the simplification of the square root of 8. It's like pulling out the perfect square of 4. So you could kind of think about this instead, if you wanted to, as being the square root of 8, or 8 to the 1/2, if that helps, thinking about it as like that, square root of 8, or again, thinking about it as 8 to the 1/2 power. And maybe even thinking about it like this, 1/2 raised to what power is equal to 8 to the 1/2. Okay, does it feel like we're getting anywhere with this? Okay, so then 8 is really 2 to the 3rd. So this is like saying 2 to the 3rd to the 1/2. Okay, now I feel like we're making some progress. And that's going to equal 1/2 to the question mark. Well, we don't know what the power is. So I'm just using this question mark to kind of represent another variable, like my unknown, the thing I'm looking for, right? That really means then this is 2 to the 3/2. Remember when you raise a power to a power? And that equals 1/2 to what power? Well, okay, so this is 1/2 and that's 2. If I wanted to make this be instead 2, I'd have to have a negative exponent on it to flip it. And so if I just think about that, flipping that, I'd have to make the exponent negative 3/2. And so kind of long story short, this would be a negative 3/2. So if we took the 1/2 and we raised it to the negative 3/2, the negative would flip it and make it 2. And if I raise 2 to the 3/2, of course you can see we get 8 to the 1/2, or the square root of 8. So that one was a little tricky one. That one, long story short, that one was much more difficult. Taking a look at the ones that we've done so far, all the powers of 10, the base 10s, and the base 1/2. I want you to take a moment and pause the video and try the U-turn questions, and those are for log base 7. So we're looking for powers of 7. So 7 to what power would give us each of these outputs. And so go ahead and take a moment, pause the video, and try the U-turn questions. All right, so log base 7 of 343 is 3 because 7 to the 3rd is 343. The log base 7 of 149th is negative 2, and that's because 7 raised to the negative 2 power is 149th. And then finally log base 7 of the square root of 7 is a half, because remember, taking the square root is like raising something to the half, so that would be 7 to the 1/2 is the square root of 7. And it just kind of helps if you kind of read it in a circle. You just say, okay, the 7 raised to what power gives me 343, and so on. Now you may have noticed that on your scientific calculators, just basic ones, graphing calculators, whatever, you may have seen a key that looks like this before. And that actually is the logarithm. But that's specifically the log base 10. That's also called the common log. So the common logarithm, because that's what our number is based on, is base 10. And so when you see the log without a base listed, it means base 10. So it's implied that it's a 10. But there's also another logarithm key on your calculator, and it's this one. And this one is actually the natural log. And, or I guess it's log natural, because the L is first. And that actually is like saying log base E. And so instead of the common log, which has base 10, the natural log is base E. So that's, that E, that number we've been talking about that approximates that continuous growth and decay, that 2.718, that, growth constant there, is the base here. So it's asking if you raise E to what power will you get this result. And so those are the ones that our calculator is programmed to evaluate. And so if you have base 10 or base E, you can, instead of having to kind of think your way through it like we did these base 10 ones up here, we could have just simply typed in log of 1000, and when we hit equals it would have said 3. But what that does is allow us to maybe evaluate for numbers that aren't really easy to figure out, or maybe they're not even going to be nice integer or even fractional powers of a number, and so it allows us to then approximate the exponent that we'd have to raise this number to get, or the base 2 to get this number. The directions for this example say use the scientific calculator to find the common logarithm and the natural logarithm of the given number, and verify each result by evaluating the appropriate exponential expressions. So for example, if I did log 13, it's like saying log base 10 of 13 is, and I'm going to type that in my calculator. So I got approximately 1.114. Now I didn't get an exact value here, like an integer or even a fraction or whatever, but that's because I'm talking about raising 10 to some power, and getting 13. And I know that if I raise 10 to the first, of course I get 10. 10 to the second would be 100. So it's got to be something between 1 and 2 as an exponent, and that actually would work. So if I took 10 and raised it to the 1.14 power, I would get approximately, I got 13.0016957. And so again, that's almost 13. It's approximately 13, just a little bit over 13. And again, anytime these don't come out nice integers, when we go to check them by putting them in exponential form, they're going to be close, but not perfect. So then what about if we did the natural log? So if I did the ln of 13, so now what I want to know is really what is, if I raise e to what power will I get 13? So that's really what I'm asking for. We don't usually write the e here, just like we don't really write the 10 here. But it would be asking me that question. And when I did that, I got 2.565. And so what that's saying is if I raise e, which is about 2.718, to the 2.565 power, I should get about 13. And so I'm going to go ahead and do that on my calculator. I'm going to raise 13 to the 2.565 power. And when I did, oops, not 2 times, but e to the, sorry, not 13. When I raise e to the 2.565, I got about 13.0006583, which is pretty darn close to 13. So why did I get a different number when I did the natural log versus the common log? Well, because with natural log, I'm looking for the power that I'd raise e to, which is a much smaller number than 10. It's 2.718. So the exponent is higher because I'm raising a smaller base and still trying to get 13. So, those are the keys that your calculator is equipped to already do. Let's go ahead and designate B for you try, and just want you to write and verify the common log of 0.42. So again, you're going to do log base 10, which is the key on your calculator of just 0.42, and just write down what the exponent will be that you'd have to raise 10 to get 0.42, and then the natural log of 0.42. And again, you can take a moment and verify that by raising those bases, which in the first is 10, and of course in the second one is e. Just raise to whatever power you get, and make sure that you get approximately 0.42. Pause the video now for the U-try. And hopefully you found that when you raise 10 to the negative 0.377, which was what you should have gotten for the common log of 0.42, you'd get approximately 0.42. And when you raise e to the negative 0.868, you should have gotten again approximately 0.42. So our final topic today is we're going to take a look at evaluating a logarithmic model. So logarithmic models are used all throughout real life. So for instance, common uses of logarithmic scales are when you have very large range of numbers. So very, very large numbers, very, very small numbers. Some examples would be like strength of earthquakes. You may have heard of the Richter scale. That's a little bit outdated now, but that's based on logarithmic scale because, again, it's measuring the energy that's released by an earthquake, which can be extremely large amounts of energy. Sound loudness, light intensity, and pH of solutions are just to name a few. So speaking of pH, in our first example, the acidity level, or pH, of a liquid is given by the formula pH is equal to log of 1 over H positive, where H positive is the concentration in moles per liter of hydrogen ions in the liquid. So notice that on that logarithm I did not see a base listed. That means it's the common log, or base 10. So in a typical chlorinated swimming pool, the concentration of hydrogen ions range from 1.58 times 10 to the negative 8 moles per liter to 6.31 times 10 to the negative 8 moles per liter, what is the range of the pH for a typical swimming pool? So that means we got to calculate the high end and the low end for the pH here using these positive hydrogen ion concentrations in moles per liter. So if we were to type in the log of 1 divided by 1.58 times 10 to the negative 8 in using our common log on our calculator, we'd find out that that comes out to about 7.2, which is, a number in that typical range for pH. And then for the next one, oops, I flip-flopped those. I put in the other one first, so sorry. That one, 1 divided by 1.58 times 10 to the negative 8, that actually would give me 7.8. And the 1 divided by 6.31 times 10 to the negative 8 gives me 7.2 pH. So you may remember that the pH scale, it measures how acidic or basic a substance is, and pH stands for potential of hydrogen is actually what it stands for, pH. And so the values range from 1 to 14, with 7 as the middle or neutral point. Values below 7 would indicate acidity, which increases as the number decreases, 1 being the most acidic. And so both of these numbers are really pretty close to neutral. 7 would be neutral, so they're a little above neutral, so they're a little more on the basic side. They're not on the acidic side, just a little above 7. So again, the pH would range from 7.2 to 7.8 would be the pH range for the swimming pool. Let's go ahead and turn the page, and we'll look at one or two more examples. Okay, so Lactobacillus acidophilus, that's how I always pronounce it, is one of the bacteria used to turn milk into yogurt. You may kind of hear that on commercials, probiotics and all that other stuff. But anyway, the population P of a colony of 3,500 bacteria at time t in minutes can be modeled by the function P of t is equal to 3,500 times 2 to the t over 73. How long does it take the population to reach 1,792,000? So now we've looked at stuff like this, and we've even solved something like this. We used the graphing calculator. Today we're going to try to see if we can evaluate this using our calculator. And so I know that if I were to take and plug this population in here, 1,792,000, and set it equal to 3,500, which is the starting amount, must be its doubling, every t divided by 73, and remember t meant the time in minutes, so t divided by 73. So rather than using our calculator, what we're going to do is try to solve this a different way, algebraically. So first thing I could do is I could divide off this 3,500. So I'm going to divide both sides by 3,500. And when I divide the left side here by 3,500, I get 512. And on the other side, what's left over is I have 2 to the t over 73 power. Now, if I wanted to solve for t, I'd have to try to get that t out of the position of the exponent. Well, here's where logarithms come in. If I rewrote this as a logarithm, I'd say log base, well, the base is 2, right? And the power it's being raised to is the t over 73. So I put that power all by itself on the other side, and my result is 512. So what that's really saying is if I were to take 2 and raise it to this power, I would get 512. And although it's not a super common one, I do happen to know that 512 is a power of 2, so I just kind of did a little guess and check, and I found out that it was 2 to the 9th power is actually what 512 is. So basically what that's saying is if I wanted to raise 2 to the t over 73 power and get 512, that t over 73 would have to be equivalent to 9. So that means that t over 73 must equal 9. And then I could find out what t is by just multiplying, or do the cross products or multiplying both sides by 73, and I find out that t must be 73 times 9, which is 657. So I'd find out that the time in minutes would be 657 minutes. Or I guess that would be that's in minutes, and that would be in hours, approximately 11 hours. If I divided that by 60, actually 660 would be 11 minutes, so it's just a tiny bit under 11 hours. Now we're going to save these final 2 questions to do in class. And so the next time I see you, we are going to try these in class as some warm-up questions. So that does it for today in our little introduction to logarithms. And there's so much more great things to learn about logarithms, so just that'll have to wait for another lesson. Thanks for coming to class.